There's one more kinematics equation we need for one-dimensional motion like this, and that is, let's accelerate for a known distance delta x rather than time t. Or we could say delta t, but as I said, delta t is sort of redundant. So if you accelerate, so a problem might say something accelerates as it falls 10 meters and ask some questions. And you think, well, I don't have t, what do I do? So we're going to look at what happens, how do you get rid of t? And then what equation do you end up with? So it could be something like this, like we've been doing over there, where we have our ball and it starts at one place and it ends at another, and all we really know is delta x, and we know its acceleration. Right? So it's really just like we did in the last demo. We started out at some initial position, whatever it might be, and we give it a push. It might have an initial velocity, but now we say stop here, and we look at the distance. It's how far it went is what is as a known, rather than how long it took it to get there. That's the kind of case that we are thinking about. So let's see how we would figure it out. So let's see, at constant acceleration, which we are assuming constant acceleration, at constant acceleration, what do we get? We know that a is going to be the velocity it gets to when it's here minus the velocity it had initially over this time that we don't know. All right? So here it was at v naught, here it got up to some v. Faster value because it was accelerating. We only know delta x. Okay, so there's a problem. We don't know t. We know a, we don't know what the velocity did either. So we've got to figure out what are we going to use for t. So we say, how long did it take? How long did it take? Because we know that there is some average velocity. There has to be an average velocity. And we know that average velocity is delta x over delta t. So we could write it this way, that delta x is the velocity average, because this is a complicated motion, times time. Right? So we could replace that t with this, the delta x and the average velocity. But we don't know the average velocity. How do we get, what's the average velocity? Well, under uniform acceleration, v average, in this case, it's really just sort of a time-weighted average of all the velocities between v naught and v. So it's really, in this case, it is the average. It is v naught plus v over 2. It's the average of those two numbers. Earlier when we calculated it, we had two different trips, and they might have been different uniform velocities for different times, and I said you can't just average it, but in some cases you can. If every trip is the same amount of time, then you just average them. If it's a uniform acceleration over a constant amount of time, then you just average the two endpoints. So there are times when you can simply average. So if we put all this together, what are we going to get? Let's see. So we're going to plug in, let's see, a equals v minus v naught over t. But then for t, we're not going to put t, we're going to put delta x over v average. So I'm going to put delta x over v average. So v average is going to end up in the numerator, right? And what is v average? It's v plus v naught over 2. So I'm going to put it in the numerator, v plus v naught over 2. Right? All that shows up. Get those, that times that, and then you start to see something interesting here. We can bring the 2 and the delta x over here, so we have 2a delta x, and then we have sort of a minus b times a plus b. that's the difference of two squares, if you remember from your algebra. So this is actually equal to v squared minus v naught squared. And if you don't believe me, do the FOIL method, right? First, outer, inner, last. But the cross terms cancel, and you have v squared minus v naught squared. And then you put it all together, and this is a way to solve for how fast is it going. Is usually how this is written. How fast it gets to is this. V squared equals the initial velocity squared plus 2ad. 2 times the acceleration times the distance over which it accelerated. So that's an equation you use a lot in kinematics. When you look at it, it's not real intuitive exactly where it comes from. Basically, it comes from combining a few of the other equations. And it is also a constant acceleration equation. Okay? So we'll see how to use this equation in a few problems.